fell. And so it's the 0.3 is how far it fell, but that's not the number I want when I calculate its gravitational potential energy. So this needs to be a 0.7 here. In fact, if I do the arithmetic here, you'll see that this comes out to be 7 joules. And so I still have some algebra to do, but I'm hoping you see here that this is what it's saying here, is that at that point right here, after it has dropped 30 centimeters, it still has 7 joules of gravitational potential energy. So it lost some, yes. In fact, it lost 3. It had 10 joules of gravitational potential energy. And now that it's fallen a little bit, it has 7. So that means this right here, the 1/2 mv squared, see, in that way, the kinetic energy of 3 and the potential energy now of 7 add up to 10, which is the same total energy it's supposed to have all the way down. And so again, notice it's losing potential energy as it goes down, but gaining kinetic energy, so the two together always add up to 10. Now if I keep going with my calculation, I can put in a 1 kilogram. I can then move this over to here, and so that 3 and that 2 is going to become a 6. That joule divided by that kilogram is going to leave me with meters squared over seconds squared, so that's going to be velocity squared. And then finally taking the square root, so I'll need a calculator here, and the square root of 6 is 2.45. 2.45, and then meters per second. Take the square root of your units. And so I could answer that question about, okay, what is the speed after it has fallen 30 centimeters? And hopefully you see in this, because we won't have time to do every combination, but couldn't you have answered this question if they said, what is its speed after it fell 70 centimeters? After it fell 90 centimeters? All you would do is to take the energy you start with is equal to the energy you end with. That's the important point. Conservation of energy. And now we just have to keep track of our 3 energies. The kinetic and gravitational potential are the 2 I was just focusing on. But maybe I should say a little bit more about heat, because watch this one again. This is kind of fun to see, and I probably can't even see it on the ground, but it does start up here with 10 joules of energy, and it's all gravitational potential energy. And so as it falls, it loses the gravitational potential energy, gains the kinetic energy, but then eventually it hits the ground and it rolls and slides across the ground, and right now it has come to a stop. So how much energy does it have now? Remember, it has no height and it has no speed. How much energy does it have? And no, the answer is not 0. It's still 10. Because where is that 10? Heat. The rubbing across the ground as it slid across the ground is going to make the molecules start to move. And so if I did it this way, and said, all right, let's look at the motion from the very beginning, when it's at the top of the table, to all the way to the very end where it is slidden, not only hit the floor, but it's sliding across the floor, and it has come to a stop. This rope's a little bit in the way. Maybe I'll just point out that 10 joules, again, is what it has at the top. Then when I go to calculate its potential energy and its kinetic energy, and now that I know that there's been some rubbing going on, I have to include the third piece of energy, the heat energy. And in this case, I know it's on the floor, so the height is 0. I know it has come to a stop, so its velocity is 0. And so that would tell me that the amount of heat energy is 10 joules. So 0 potential energy right now. 0 kinetic energy right now. But it still has a total of 10. Those molecules are moving. Although, in all fairness, those molecules by now have probably bumped the air molecules. And so that 10 joules of energy probably is no longer completely in here. Maybe there's still 1 or 2 joules still in here. But when it got warm on hitting the impact, it now has kind of warmed the room a little bit also. But that total energy is still there. It's just somewhere else. It's either in another object or it's in another form. Now, there is a couple of other little things that I thought might be good to kind of wrap up here. Some that are in the chapter and some that aren't in the chapter. Let me start with one that is not in the chapter, because I want to emphasize something bigger that we're going to keep doing as the semester goes along here, is that this principle of conservation of energy is true for all forms of energy. And at this point, we are only really discussing 3 kinds of energies: the kinetic, the potential, and the heat, the gravitational potential. But there are other forms. There is electrical energy. There is what we call chemical energy. There is sound energy. There is nuclear energy. And all of those we're going to add to this list here. But it's why I brought out this little apparatus here that I was trying to be careful with when I was trying to move this out of the way. Because this is a good example of electrical energy and chemical energy, both of which are very common in the world we live in. So I thought I would throw them out there now in this chapter, even though your author is going to wait a little bit before he introduces those. He considers them more of a more advanced topic here. But you might have been asking back here, kilogram mass, when I picked it up right here, and I said it had 10, and then I said it kept having 10 all the way down. You might say, well, where did it get its 10? And I would say it got it from me. I lifted it up. Okay, well, where'd you get your 10? See, and this goes on, and in this case, I got my 10 from the food I am eating and digesting. And so through a process, if you've had biology and the whole chemical process of the ATP and the ADP and how it, makes my muscles contract here and gives it that energy, I would say that's a chemical energy. In other words, there is a chemical energy in the food that I ate. And that's where I got it. And so my effort of lifting it up, in terms of exercise science, you would say I'm burning calories. I am giving it my energy. And the calories is a measurement of how much energy I have. We'll hear that word later on, but calories really is a certain number of joules. It's a certain amount of energy. And so by me eating my, I had Cheerios this morning, and so the Cheerios I have right to here. All right, which of course, question here, Cheerios, which is made from oats, where did it get its energy? Well, that was from the sunlight. I get it to the sun. Where does the sun get its heat? Well, the nuclear energy. So there's this whole process of energy is being conserved. But a big or two big types of energy in the world we live in are the chemical energy, all the food we eat, those batteries that you love to use to charge up your cell phone. That is that lithium ion, and so you have a lithium atom. And when the ion is, or when the electron is free from the lithium, it's an ion that takes energy. When it goes back, it then releases that energy. And so that's a chemical energy. And so what you do with your cell phone is you probably plug it in at night, and you're taking the electrical energy and you're converting it into a chemical energy, which then hopefully that chemical energy goes the other way and then makes electrical energy. Then hopefully makes light energy, so you can see the screen on your phone here. And so there is no creation energy. It is this changing of the forms of energy one to another, and that's what this little machine here is doing. It's not the most exciting machine, but it is plugged in. And so I'm taking electrical energy, which again you might say, well, where did it get its electrical energy? Well, I just plugged it into the wall. But where did Edison get that? Well, there's a lot of different places. Well, I'll just say maybe they're getting it from Hoover Dam. And so Hoover Dam has this water flowing through it. And so the kinetic energy of the water flowing through the dam is then converted into electrical energy, which of course, well, where did the water get its kinetic energy? Well, it got it from the gravitational potential energy, right? It started at the top of the lake, and they let the water fall through the dam and through the turbines. Okay, so where did the water get that potential energy? Well, I'd say it got it at the top of the lake because it came from higher up in the mountains. Okay, where did it get that? Well, it came from the snow, which came from even higher. Okay, where did it get that? Well, that was the evaporation, and so maybe the water started actually in the Pacific Ocean. And the sunlight hit it and gave it its energy and evaporated it and lifted it up. And then it blew inward, and then it fell into the Rockies, and then the Rockies flowed down into the Colorado River, which then got behind Hoover Dam, which then made kinetic energy, which now I have that energy right here. And of course what I'm doing here and trying to illustrate, and maybe taking much time, but to show you here that there's other forms of energy. This little apparatus, and it's a slow apparatus, so I won't show too much here, but the electrodes of the electricity are hooked here, and here I have the negative, and so that should be attracting then the H's in H2O. And so what I'm really doing here is taking electrical energy and ripping or tearing the water apart. And if you know anything about water, water's H2O, and so it's made out of water and oxygen, and so I'm pulling it apart. Hydrogen and oxygen. And so water's H2O, and so I'm pulling the hydrogen and the oxygen apart here. And as I pull them apart, I will get bubbles that come up here, and in my case they're kind of slow, but I've got a few bubbles up here, and I do notice I've got twice as many up here as over here. And so there's a little gap. So this whole thing is filled with water, and the bubbles are coming up, and so this is my hydrogen. And so last night I let this thing go all night, and I made a lot of hydrogen. And so last night I was converting electrical energy into chemical energy. I did the same thing with my cell phone. I actually did that with my car that broke down. I took the battery out, I put it on the charger, and all night long I left it on the charger. And in that case I was converting the electrical energy that was in my garage into a chemical energy. And in this case it's car batteries are a sulfuric acid and a lead oxide mixture. And so I was storing that in the chemical energy. Well, I say all that because I took that hydrogen and I put it then into this balloon. And so now all of that energy that was electrical energy has now been stored here as a chemical energy, which then will give me a chance here to show you conservation of energy, because this hydrogen then, with its stored energy, can be re-released. And so if I put the oxygen back to the hydrogen, there should be a release of energy. And so in this case, I'll just do a burning, an explosion, if you will. And so I'll take a little match. In fact, I'll take 2 matches, light the second match. But the important match is the one on this stick, so I can stand back here a little bit. But once I put this match to that balloon, it will then start a chemical reaction that will release that energy. And so again, just like your cell phone, all night long you were charging it, you were then taking the electrical energy and converting it into a chemical energy. And now today, you are probably doing the reverse. You are taking that chemical energy, that lithium, now that it, and making the reaction inside the battery. Or maybe you're starting your car, so you're taking your sulfuric acid and your lead and you're reacting them, getting water and lead oxide. And as you react those, you then release that energy. So in the car, you want that electrical energy to turn over the starter motor, which starts your car. In your cell phone, you want that electrical energy to run all the electronics inside, including this screen, which gives off light so you can see what's going on here. And so this is my way of just kind of having fun here with conservation of energy, with some energy that I think is good for you to see, even though it's not the 3 that we're talking about here. And I just like to blow up the balloon. So I'm going to just stand back a little bit and blow up the balloon. And so there's our conservation of energy. Now, there are some other little things here that are in the book that I should point out. You've probably noticed this other set of wires that are hanging. It's actually a rope and a pulley system that is hanging from the ceiling here. But it too is a really nice way to talk about conservation of energy. I like to put some numbers with it here, or at least some ideas. And so if I were to start down here on the ground level and climb that rope up to the ceiling, or maybe not all the way to the ceiling, but near the ceiling. Maybe I'll go 2 meters, let's see. Well, if we take my center of mass, maybe here. So maybe if you imagine me going up 2 meters, you might say something like this. So I'm going to go up 2 meters. The amount of energy for me to go up 2 meters, mgh, would be, and so I'm about 75 kilograms. G is roughly 10, and I'm going to go up roughly 2 meters. So 2 times 75 is 150, and then another 0 is 1,500 joules. So it's going to require 1,500 joules to get to the ceiling. All right. Do I have enough energy to do that? Well, yeah, 1,500 joules maybe sounds a lot. The typical human on a typical day eats about what a nutritionist would call 2,000 calories. 2,000 calories is about 8 million. So this is small potatoes in terms of energy. I have plenty of energy to get to the ceiling. All right, so here I go. I thought I had enough energy. I can't seem to do it. And what I want you to be careful with here is it's not that I don't have enough energy, it's I don't have enough force. Don't mix force and energy. You see, for me to lift myself up 2 meters, it's true that I would have to burn 1,500 calories to do that. And I'm trying to emphasize, I've got plenty of energy. What I'm lacking here is enough force. And my arms aren't strong enough to lift me up. I can barely get off the ground. And so instead, I've got this pulley system. How does that help me get up? Does it take less energy just because of all these ropes around the pulley? No. That's what I want to emphasize. It takes less force, but not less energy. Watch. If I were to try to lift myself straight up, the amount of force would have to equal to mg, which in my case, as I said, is 75 kilograms times 10 meters per second squared. So I would have to have 750 newtons of force. And I would have to apply 750 newtons of force for however long it takes me to go 2 meters up the rope, and I would burn this much energy. But these are the condition, and there's 2 of them for me to climb that rope. I've got to have this much energy, so do I have enough energy? But I also have to have this much strength. I have to have this much force. But if I did something like this pulley, and if you look closely at this pulley system in a second here, there's a little chair, and there's a string that goes up and around the pulley, and then around the pulley again, and then around the pulley, and I'll just pull it to one side. And you can see that when I have this. And so if I just pull this up, I'm hoping you'll begin to see, and looks like I got it all twisted here. I'm hoping you will see that these 3 ropes really are magnifying my force by 3. So in other words, if I pull with 100, I have 100 here, 100 here, and 100 here, lifting it up. And so this pulley system is magnifying, if you will, my force, requiring me to have less force, but not less energy. Again, let me emphasize that. And let me just kind of done with this for today. Take this down. Get it out of the way. Well, what I'm trying to emphasize here, and in my case, I'm going to actually sit on the chair, and so this rope is going to come down to here. And so this, what we call a Boltzmann's chair, is going to be then a way for me to amplify the force, but I want to keep emphasizing that I can't change the required energy. And so the work to get up to the ceiling would be force times distance. But watch this. I could have a big force and a small distance. And that could be the same number as a little force times a big distance. And that's really what this pulley system is doing. That is what any leverage system does. It says that you're going to lift something up, you need a certain amount of energy. Now, if it's a machine, an electrical machine, we could get that energy from the electricity itself, like an elevator. When we go up an elevator, you know, and we've got to go 100 floors up the elevator, that energy comes from the electricity running the motors on the elevator, and it doesn't come from us, so we don't feel like it's the same energy, but it truly is the same energy, just didn't come from us. But if you take away the electric motor, you could actually lift something up with a small force if you change that to a big distance. And I hope you kind of see it in here. When I wrap it around a bunch of times and I pull on it, watch how far I have to pull the rope for this thing to go up 2 meters. And so I get a lot more distance in the rope, but a smaller force, and it gives me the same energy. Well, I hope that made sense, because this is just a long way of saying I really have 2 options to go up to the ceiling. Option 1 is pull with 750 newtons all the way to the top, which I don't think I can do anymore. I'm too old. But the other option is to reduce the amount of force by a factor of 4. And so whatever 750 divided by 4 comes out to be. And so if I have reduced the amount of force by a factor of 4, then I could get that same energy by increasing the distance by a factor of 4. And that's what's going to happen with this little chair system. Watch. If I just kind of stand and sit in this little chair contraption. Let me just kind of get it on up here. All right, am I back on? Sorry about that. I knocked it off. Let's see if let me just put it in my pocket for this and let's make sure I don't bump it off here. Okay, so if I come back to here and put myself in the chair, I want you to see that I could actually lift myself up with one hand. It doesn't take much force at all to lift me up. It's actually really easy. But you will also hopefully see that I pulled the rope a lot further. And so I have less force, more distance, but the same amount of energy, the 1,500 joules, to go up to that ceiling here. And so be careful with the difference between energy and force. And so that's an important subtlety in here. All right, I'll fix this up again. So still hear me? Okay. So one more thing, and then we'll call it quits here. We better get started in the next chapter, because the next chapter is kind of long, and I want to make sure we jump into that next chapter before we take our break. And so we'll have a little bit done, and then the break here. But the last thing that your author says is, what about the rate at which the energy is being done? And I lost my black marker somewhere. Oh, here it is. And so let me put here rate of energy. And so I'll say it again, the big picture of this chapter is conservation of energy. And if we come back over to here, remember I kept pushing this off, And I kept saying that as it would go down, its total energy wouldn't change. That it had 10 at the top, and it even had 10 at the bottom, it even had 10 in the middle. But if we look at one type of energy, that does change. In other words, it loses potential energy. And so if we do this kind of thing, we say, okay, what is the change of energy and the time taken? We might say that it loses 10 joules of potential energy as it falls. Well, the rate then would be how long did it take for it to fall that 1 meter? And I think it is about 1.25 seconds. Maybe I need to grab my calculator here. 2 divided by 10 square root a meter. 2 divided by 10. Oh, bummer. Be nicer if it was a little higher in height, but I'm going to go with that number. It's way less than that. But I wanted you to see that the rate is the change in energy and the time taken. And so in this case, if it took 1.25 seconds to fall, which it doesn't even take quite that long, but it would be 10 divided by 1.25, which comes out to be an even 8 joules per second. In other words, as it's going down, it loses 8 joules of potential energy every second, which of course it lost a total of 10. That's why it took more than 1 second. And that's why I wanted to use a number that was more than 1 second. But this has a name. We call this then power. Capital P for power. And so how energy changes with time is then referred to as power. So in this case, as it is going down, I would say the power is 8 joules per second. And as I mentioned at the beginning of this one, this chapter, the units from here forward are often given name to honor the great scientists in that field. And so this is named in honor of the inventor of the steam engine. And so it's called a watt. James Watt. And so 8 watts would be the answer to how much did the potential energy change each second. Oh, let me try another one here. What if it was this? What if it was already on the ground? Okay. So it's sitting on the ground, and I go to pick it up. And I could pick it up kind of slowly and put it up here. So maybe that takes me 2 seconds to do it. Or I could pick it up quickly, and it only takes me 0.5 seconds. But whether it takes me 2 seconds or 0.5 second, I am giving it 10 joules of potential energy. And so quickly or slowly doesn't change the amount of energy, but it does have a different rate. So you can see, hopefully, that rate isn't really that hard. It's really nothing more than, or nothing different than, talking about speed and accelerations, where those were rates of movement. This is not a movement, but this is a rate at which the energy changes. And so if I did it fast, versus slow. Fast would be 10 joules in a half a second. Slow would be 10 joules in 2 seconds. And I'll say it again, notice both of them are 10 joules. I am adding 10 joules to that object just by picking it up and putting it on the table. The power is the rate. So in this case, this would come out to be 20 joules per second, and this rate would come out to be 5 joules per second. And hopefully that kind of makes sense, right? 5 joules per second means in 1 second you give it 5 joules. So in the first second you give it 5, and in the next second you give it another 5. So that's a total of 10. Whereas over here, this is saying you're giving it 20 joules in 1 second. So if you moved it for a whole second, that would be 20 joules. But I'm not doing a whole second. I'm only doing a half a second. So if the rate is 20 joules per second and I only lift it for a half a second, that means I would put in a total of just 10 joules. Right, so both cases are 10 joules. The rate, though, is different. And of course, we would write this as 20 watts, and we would write this as 5 watts. And so I'll say it again, especially since the word watt might be common to you. Watt is a measurement of the rate of energy. It's the number of joules per second. And so you might have come across the word watts associated with maybe a light bulb, or an electrical oven, or an electrical microwave. And I think because most people have come across the word watts with electricity and electrical power,